Okay, so let's get started. So in the previous lectures we talked about linear model and linear classification and then regression. And then we saw a little bit about nonlinear transformation, how we're gonna transform a nonlinear data to a linear one, right? And then apply the linear method that we already know. Let's just have a recap of what we've discussed in the previous lecture. So we talked about the transformation function of phi here. We call it a Fisher transform. So it's going to transform your data from X space into Z space. So staying here and looking at the other space, you're going to see it nonlinear. But if you're inside that space, you're going to see that linear, right? That's why at this point you can have a linear classifier to classify your classes, right? So from there, you're going to see x1 square and x2 square, but here you're going to have only z1 plus z2 equal to 1, right? And so that was pretty much the high-level process of starting from a nonlinear class separable data, apply the transformation, bring it back to a linearly separable, and then apply a classifier such as PLA here. And then coming back, if you do the inverse, it's as if you're looking from here to here. So you're going to see that as if you were doing it this way, in a circular way, which is definitely is not a linear classifier, right? So the W tilde of PLA would become something like this. So up until this point, we were talking about two main models, right? Let's talk about the third one, which lays the ground for us to go further with multi-layer perceptron and later on neural network in a few weeks. So we call this logistic regression. So coming back to the previous problem, say you've got a continuous signal, right? We call it S here. Let's think about that as a signal that is incoming. By doing a linear classification, right, our hypothesis of X is going to output the same sign, the same signal in a sign mode. So either 0 or 1, right? As if you're slashing it to 0 up until this point. So all the minuses are going to be 0 on the output, and all the pluses would be 1, right? So these are your incoming data, x artificial coordinate of x0, having the w0 weight. So we can represent it this way now. Then so these are your data, x1 up to xd, d-dimensional data. Each of them has their own w, w1, w2, up to wd, right? So they are coming this to our classifier, and as you see, as the shape suggests, the output would be our hypothesis of X, right? Is as if we are slashing it to two levels, and so minuses and pluses. The way we defined the loss function was an identity output or function for all the y's that were not equal to the output of the sine function, right? The sine was a W transpose and X, so that was the output of this W transpose X, right? So that was the loss function. That was our first model. Now, in a couple of lectures ago, we started learning about linear regression. So we have the same situation, but instead of having two levels in the output, it's as if we sort of linearize the output. We just flattening it out in a linear way. So all the ways, again, starting from x0 and w0 corresponding to that, and x1 up to xd comes there, and our sign is going to output it this way, and that would be our hypothesis of x, right? The way we computed the loss function was using square error. So the difference between your actual label with the one that our hypothesis X was calculating, right? And we mentioned why we are using a square way rather than an absolute, value for that. Now let's talk about the third one, which adds a little bit of complexity to the problem and makes it very interesting, and that lays the ground for many different machine learning models after that. So what if instead of slashing it minus and plus, or just outputting it in a linear way, what if we were playing it around and smoothing it using this sort of stretch and flattening out S sort of output, right? So we call this sort of output function a sigmoid. So the sigmoid function has a lot of unique features. So it is defined as a theta of S, which is a signal. So it's going to be the e to the raise of S divided by 1 plus e to the raise of S. It sounds very wordy and then sounds complex, but it's actually pretty simple to understand. And the way they have been defining it this way is actually makes it very easy to take the derivations from. And we'll see that in a couple of lectures, why we are using such kind of way. There are so many different things rather than sigmoid that we could have used, and we gradually get to understand and get to know them one by one, perhaps some of them in neural network later on. So now, if we use S here, in this case, our theta of S, which was a sigmoid function, is going to output this way now. So the output would be surrounded from 0 to 1, right? And where X is 0, you're going to have half, right? As I mentioned, we call it sigmoid or a flattened S, or a soft threshold, right? We can call the previous two, especially the linear, especially the classification one, the perceptron one, a hard threshold. It would just making it hard minus 1 and plus 1. But this is sort of a flattening out and making it softer, right? From 0 up to 1. And you soon understand when we have all the values in the output from 0 to 1, we are actually dealing with probabilities, right? So the interesting point about logistic regression is the output, we can actually deal with probabilities. And another interesting point about this, now that we have probabilities in the output, can we use those probabilities to come back to data we used, right, before we got threshold by that soft threshold, right? So now we have two interesting problems to see. First of all, when we have an input, we apply S, what's going to be the output, right? The y hat. This is the classic prediction we're talking about. Now, having these probabilities from 0 to 1 in R space, can we use this and bring back an estimate what were the x's, right? So this way, if we go, it's going to be the prediction. When we come back here, there's a famous statistical method, we call it maximum likelihood estimation, MLE, or log loss, or cross entropy, or so many other things that we discussed some of them today. So that way, from the data to the prediction is the classic thing that we're talking about. But when we have that probability, having had that, are we going to come back to the parameters of the data to estimate the maximum likelihood of that? So these two are going to be two interesting problems. So as an example, let's just talk about a simple example that we can tackle with, logistic regression. In the past, we've been talking about some problems like having this feature vector of patients, like age, residence, I don't know, gender, I mean, not residence, but like gender, age, I don't know, heart rate features. Is he, I don't know, prone to just have a cancer or not, 0 or 1, right? But now, using a logistic regression, we can define so many other more intricate problems, like finding a risk score of a heart attack given X, right? As cholesterol level, I don't know, age, weight, and so on and so forth, right? So now we can just output sort of a probability here as a risk score, right? I don't know, 20%, 30%. So this makes it more applicable to many other, is easier to understand or word, problems. Let's see. Questions?
So like the previous slide, the first slide. So like this S is we used to map our WTX to our output is used to map our input to the output.
Yeah. So S is actually our predictor, our hypothesis. H, right? S is the here is our hypothesis H that we picked from many hypotheses that we had. I don't know, N within the capital H of all the tools that we had, right? So the one that we use and apply it on data is S, right? It's as if you input your data in either way, here, here, here. And then how are you going to output that, right? Are you going to output that? Are you going to apply a sign? Are you going to just output it like this in a linear way? Or you're going to apply it using a theta of S? Later on, you're going to see in neural network that we call this process activation, right? So we input the data, we sort of activate them, and get an output out of those. It's as if some of the data are activated one way, and some of them are activated the other way. Like you just slash them 0, or just you make them 0 to 1, depending on the type of the function you're applying to. Okay? All good? All right. So now we can define, if you want to calculate the risk score of a heart attack, given those features, our theta of S would be probability of a heart attack, right? This makes much more sense than just if we define it like if the patient will have heart attack or will not, right? We're gonna say like 80% chances are like he might have. So the output of the S would define us a risk score, right? This is the way we can use it. Is it clear? Okay.
On previous slide, the first slide.
Did I have a typo?
The sigmoid, is that the sigmoid function that one e to the power minus is upon?
Yeah.
So, but the sigmoid function has the form 1 upon 1 plus e to the power minus s, if I'm not wrong.
What is it?
1 upon 1 plus e to the power minus s. But here it is wrong.
Yeah, here it should not be minus.
Should be plus.
It should be plus, not e to the power minus s.
I think it's just the way
It's
you
just
write
a
it.
test.
No,
What is it?
This is what its S's look like. It's kind of little.
Oh.
Let me see.
Sorry.
Is that negative
It's having
S?
minus
Or
S.
Negative is or positive is?
That one on top?
Yeah.
It's not negative.
Oh.
Yeah, it's good.
That was the tail of the S. Oh, did you all see that as negative? Oh, my bad. Are you talking about this?
Yeah.
Oh, I see.
It looks like negative.
Oh, like this, right?
Yeah.
Yeah, it's because of that badass tape. the tail over there. Yeah, this is a plus. Okay. Yeah, my handwriting is awful. I'm trying to just write them in LaTeX as much as I can. So that's why you see all these mix here. Some of them are LaTeX, some of them are handwritten. It's a mix. All right. So it's e to the raise of plus s divided by 1 plus e to the raise of s. Yeah, as you see here. So so now,
Professor, just a
Yeah,
question. Is risk score same as probability?
in this case, the probability of the output that has a value from 0 to 1 give us sort of a probability, and that is mapping to a risk score. Yeah,
Oh,
yeah.
so in this case it is.
Yeah. You can define risk score different ways. I mean, in general, but yeah. Okay. All right. So now we are talking about a probabilistic model, right? Animation. Yeah. Let's up here. So let's formalize it a little bit. So PR stands for the probability, right? It's a conditional probability. What do you mean by that? So it's a probability of y given the x here, and that's how we write it here. So now we are dealing with two things. Now, our y, say, is like a binary class, right? It's either +1 or -1. But the probability of y given different x's gives us two options, right? So either we're going to have f of x for the case that y was +1, or the other way, we're going to have 1 minus f of x, because it's a probability, right? 0 to 1, for the otherwise case. Now, if you add this to your theta function, so theta of x, you're going to have this on the case of +1, right? So your theta of s would be e to the raise of w transpose the vector and multiply by x, right? Divided by 1 plus e to the raise of wt x. On the other hand, for the case of -1, if you expand that, you're going to be theta of s e to the raise of minus w transpose, the same happening in the denominator, okay? All right, so now actually we can, in both way, we can simplify it with just one formula, right? So we can define it, our p hat, with the output prediction regarding the w's of y given x, can be written as simple as one of those two, because if you use minus over minus, you're going to have plus later on. So, and that defines us how we're going to go from the RD, a d-dimensional space of R, to a 0 and 1, which is a continuous space here now, right? And that's the probability we are interested in talking about. Now, the interesting is one of those two interesting points that I mentioned. One is, the question is, how do I choose the weights so that the output of this function, the theta function, reflect f, right? My prediction. And the other point was, for the maximum likelihood is, if I have an output such as this, how am I going to derive back to my x's? Okay, so let's talk about the loss function for logistic regression now. Is it clear so far? Yeah, like, yeah, you'll just, so you have, so this is your output, right? You don't have any minuses. That's your output. So if you, that's your S10, theta of S. So you input like a negative, I don't know, a million. It's going to be close to 0, the output. Close to 0. If you put like 0 as X input, it's going to be half, 1 over 2. If you put like a million, it's going to be again close to 1.
The location of input there.
Yeah. Right? Okay. Now, assume that our data points x1, y1 up to xn, yn, right, are independently generated. By the laws of statistics, the joint probability of all of those, so the probability of yn given xn is the multiplication of all of them starting from n1 up to capital N. Okay? Now, if we expand this to the number of n, you actually can represent it with an ln minus 1 over n of ln of the, again, the product of the conditional probability here, p of xn given xn. Now, it's as if that you have the same thing and you switch it to the denominator here. We knew that from before the previous slide that this is equal to the theta of the value we had given minus 1 and plus 1. And thus, finally, the loss function of the logistic regression, which is the summation of all the pointwise error is for the double D is going to be 1 over n, the summation of n from 1 up to n, ln of this value, right? Yeah, all my animations are not working well. So that's the thing we are interested in calculating for the loss function. Yeah.
Just a quick question. So this one is equivalent to that one? Like this negative 1 over n, this first term, is it equal to that product over there?
This to this?
Yeah, I mean the other one.
Yeah, we start from there and then become
And this one's equal.
yeah.
Oh, okay.
I mean, we estimate the log loss function using that, right. Yeah. We'll come back to this again in a few slides. All right. So this was the summation of all the pointwise errors, right? Let's see how we're going to calculate each of those points as a pointwise error using loss function. Like, so we call this sort of class of methods a log loss function, right? So I was mentioning in the first slide of the logistic regression that the opposite way of prediction, we can use maximum likelihood estimation to just come back using a probability to derive to the data that were used to generate that. So in general, maximum likelihood estimation, right, MLE, is a method that determines the values of the parameters of a model, right? So now, each pointwise error can be calculated as a log loss function, right? So minus log of the probability of y of that point given the vector of x of that point. This is just close parentheses, nothing else. Parentheses. So having this log loss function, we can we can actually interpret many things easier, or let's say in a different way. For instance, if the y, the label y was +1, right, and the output of your W transpose X was way more than 0, so you're going to see, because of the way the sigmoid function outputs, your loss is pretty much very minimal, right? You're gonna be somewhere on top of that flattened S, right? You're gonna be somewhere here. Right? You're gonna be somewhere here. That was 1. On the other side, if you are dealing with the -1 label, and the output that you predicted was way down here, again your loss would be very minimal, because the S that outputs this makes it very close to 0 now, right? So the difference between your prediction and the output of the sigmoid would be pretty close. So in these two cases, you're going to have the loss would be minimal. Does that make sense? You can just compare this with your linear classifier, which was doing a hard threshold like this, or a linear regression which was doing a linear like that. So that could be a LR, so h of LR. This could be, of course it's not visible, what is it, PLA, and this would be your third one. Yeah, almost. Okay. So let's see an example. Suppose all the x's are from a d+1 dimensional from R space. So the output of the logistic regression for your two cases, in one case for the -1, we computed -1, which was the y given x's, is 0.8, and the other case for the y +1 was computed as 0.2, right? So how we can interpret this? We can say if yn, right, is +1, the log loss of this function of the output of En of W, right, is going to be around 161 if you compute it using the formula that is here, right? This. Is around 161. On the other case, if Yn was -1, the actual label, right? So these were the predictions. The log loss is actually smaller in this case. Now you can see the controversy here, right? Because although the output, the output probability that the logistic function predicted given this conditional probability here in this case was higher, right? It actually made the final error smaller, because now we can say with 80% almost, we are sure that this is the output, right? So on the other side, the loss that we have is smaller, right? It's as if we are saying like 95% is going to rain, and apparently it's going to, and it will rain, so our error was like pretty minimal, right?
So were you saying that earlier that they then use that information to assign like a higher weight to those points? Is that what you're saying?
If we assigning higher weight to those points, is like we are coming back as an MLE, right?
That's
if
what
you are
the-
predicting from left to right, which what we did here,
Yeah.
this is the logistic output, right? So we can we can just play around on both ways.
Yeah.
All right. So in general, we can say assigning high probability to true labels will reduce the loss. Assigning high probabilities to incorrect labels will also reduce the loss, right? Is it clear? Okay. All right. Why we have two different? Okay. Here. Now that we define the loss function, yeah.
Like the second point, assigning incorrect label, could you like,
By incorrect label, I'm talking about the minus one, right? If you have plus and minus, right?
or like
So if it was actually minus one and you predicted that with high probability it's gonna be minus one, right? Right? It's a minus of the minus. All right. So now we have defined the loss function. We have defined it pointwise and the summation of all for all the small ENs. Now we go back to the same dilemma of linear regression. How are we going to minimize that, right? How are we going to converge to a better point? Can we have other methods such as the one we used in least squares or not? If you again, draw that, figure this on a two-dimensional sort of figure, you're going to see that your f, which is unknown, we say, assuming that it has this shape, right? This is unknown. Say we have some x's, right? By using a derivation of f, a derivation of x, right? If this becomes 0, we can actually, or if we assign it to 0, we can actually compute the gradients, just like what we did before, right? So now let's see some of the common characteristics. First of all, because of the probability and the log loss function, these errors are additive across training samples. I'll have a better figure to show you later on. We have, just like the linear regression, a regulated version using a regularizer here, lambda. You can just play around with making it of a more robust solution. And also, just like the linear regression, the E in of W is a convex function of W again. However, there is a different sort of problem here. Can anyone say what that is with respect to a linear regression? Looking at this, what does it stand out that differentiates between this and a linear regression? So that perhaps we are not able to just apply the same techniques. Any guesses? And you see, it's not linear anymore, right? And that yields huge problems if you want to solve and minimize this. So in general, we call these sort of problems not a closed solution, right? linear regression had a closed solution. That's why we could have applied a pseudo matrix to come up with the exact solution, right? Although it was large, at some point we would have to just even run out of memory, but still it had a closed solution answer. But for this, there are none, and I haven't seen any work predicting that. Perhaps there are solutions for when you have two variables only, but after that, it's very, I mean, the only way we can minimize the E of n of w is by doing iterative methods, right? And later on, we see that famous iterative method that established also in neural network, which was gradient descent, right? And it uses this notion that we're going to descend towards the local or global minima. So now, by now, you see that there are no closed form solutions for this because it's not linear, and that the W estimation of that is going to be pretty hard. All right.
Oh, Professor, one quick question. Go back to the so these three are common characteristics across all the data points?
Yes.
Oh.
You can say that. Yeah. So just like what I verbally mentioned before, when we in the probabilistic approach, when we try to find the most probable hypothesis given data, right? It's the way we applied all those x's, and you use that s to output it here, right? That was your y hat prediction, right? This is the classic prediction method. In likelihood, we go back from that prediction right? So our desire is to find the probability of data given a hypothesis. So we go back and find the probability of the data that generated that specific output of the hypothesis. Okay? So in maximum likelihood methods or maximum likelihood estimation or MLE, we normally say, thus if H is F, the hypothesis is close to F, or actually when we have H, if H was F, right, assuming that the hypothesis was F, how likely is it to get Y from X? If it was completely, yeah, I mean, if it was like, if you knew the F, first of all, you had the results before, right? But yeah, if hypothesis was close enough to, how likely is it to just get Y from X? And that's the interesting question. So, in another way, if the probability was high, assuming that H was F, is sort of a plausible assumption. Otherwise, the assumption is poor, right? Does that make sense? Okay. Just like what you saw there. So the conditional probability of y given x of fx for the case of +1 and 1 minus f of x for the case of -1, assuming that your hypothesis was equal to f given a data point, so you're going to have this. So you can exchange these two, right? Yes, assuming that our hypothesis was able to mimic the F, right? How likely is it to get those true labels from the data that we have? right? Okay, I've already presented you with the log loss function for the maximum likelihood. We see it in a few lines. How did we drive to that? So in general, maximum likelihood approach finds W's within R of t plus 1 that minimizes the conditional probability of all the labels given those x's, and all of them could be vector itself, right? So given that, we need to maximize the likelihood here. So we want to maximize the log conditional probability of this. So it's like as if we are maximizing the log loss, the likelihood of having this phenomena happening. So we can just expand this. It's as if, because they are independent data, right? We can define them as the product of the probability. So the 1 over n of log, the product of n's from 1 to n, right? Then when we have the maximization and a log, so the log product is going to be translated into a summation log, right? Does that make sense up to here? How did it come from here to there? In log word, okay? And then we can change the maximization, of course, to minimization. So now, when we minimize it, we have to add that minus there. So we are minimizing minus of log of the conditional probability. And that itself is the summation of all pointwise error, which is the loss function. Okay? This was W. Okay, so now we have defined the logistic regression, the maximum likelihood. There is another notion that is pretty close to likelihood or log loss, which is called cross entropy, which is in the majority of the cases in statistic, these two are synonymous. So there is another definition such as cross entropy error. I even put log loss in a parenthesis in front of that because they are pretty much close. So the measure of a performance of a classification model, right, whose output is a probability between 0 and 1. Right? In general, entropy is a measure of uncertainty when we are dealing with random variables. So if you have a random variable of x in general, and we have a probability, we can define the entropy of, for instance, h of x. Say x's are the random variable, like, right, as minus sum of all those x's from 1 to n of their probability of x by the log of px, right? And that's pretty much your log loss function. So it's actually the same. So it's actually a summation of all cross entropy is almost as a negative log likelihood. So they are synonymous. Let me see if I can clear this. Erase. Yep. So it's actually minus that log loss function, right? If you expand that, we have two classes on a case of binary. So it's an identity of yn equal to 1. It's going to output either 1 or minus 1, right? So in both cases, you have 1 here for the case of plus 1, and you have the rest for the case of minus 1, right? And that was the formula you saw in the, I don't know, 4 or 5 slides ago. In both cases, you can, I mean, these are different ways to just derive to that en of in sample error of W vector, right? But here, if you want to showcase how we're gonna, calculate this per point, it's as if you have a graph like this, right? These are your points on x-axis, or a vector of points in a higher dimension, right? Your data points are independent. Sometimes we call them, they are coming from an IID distribution. I always forget what the second I stands for. The first one is independent. Independent. Yeah. So it's IID distribution. So you see at each point we can define that En using the log likelihood here, right? At each point we have this now. Instead of, if you recall in linear regression, we would just flatten out and just estimate the distance. Here we are dealing with a more interesting property to play around, right?
The second I is identical.
What is it?
Identical. Like it
Oh yeah, identical. Yeah.
distributed.
Yeah, that's right. Yeah. Cool. All right. So now that we saw what are the interpretation of logistic regression, like log likelihood and then loss function, now we reach to the point that we need to minimize it, right? Otherwise, we won't have a good solution. I mentioned some slide ago that this thing is not a linear formula, right? So different W's are going to play around in a nonlinear way. So this form doesn't have a closed form solution. So the definition in mathematics or statistics is that in math, a closed form expression is a mathematical expression that can be evaluated in a finite number of operations. And in statistics, we just say that we can solve the problem, right, given a function, just like what we had in linear regression. In logistic regression, we do not have a closed form solution, right? So the only thing we can do is approximate the solution using different methods, which all of them are in the umbrella of iterative methods. So we start from one point and iteratively we are trying to find a better solution down the road, right? But all of them are approximation. It's not a closed form solution. So the one that is very well known and famous and easy to apply is gradient descent, that we start talking about it in the next lecture, and and then we gradually move toward multi-layer perceptron, which was the early generation of neural network. Okay, any questions for this? I've already uploaded this on Moodle. Perhaps I need to fix some typos again and updated it. All right, so see you guys next week. I'll post the first assignment, and we'll carry on working on gradient descent on Monday. Have a good day, guys.